This is Mrs. Palmer-Quay for the fourth video for Module 2. In this video I want to talk briefly about calorimetry. Remember that when we talk about heat, we're really talking about energy that moves from one object or one substance to another because of a temperature difference. Remember also that when we measure a temperature, we're really measuring an average kinetic energy of all of the molecules found in that substance or object. And that when we measure heat changes in chemical reactions, the unit we most often use is joules. When we measure the transfer of heat into or out of a chemical reaction or what's happening in a physical process, we are doing calorimetry. And typically we do that in a calorimeter, which is some type of insulated container that can be used to measure the heat changes without having the temperature of the outside environment affecting what's being measured. A very simple calorimeter is a coffee cup or insulated styrofoam cup calorimeter where you have something going on in water in solution and that you're measuring a change in temperature on a thermometer. In more sophisticated chemical reactions, or this is how they get the calorie content of the foods that we eat, you have a reaction happening in a container that's submerged in water. Inside this container, it's a pure oxygen atmosphere so that we have complete combustion going on. The substance is burned by adding electrical energy until it ignites. So we have some wires coming in, and then the surrounding water, the temperature change is measured and used to calculate how much heat has been released by our little sample. There are some basic assumptions that happen in calorimetry. The first one is that we are not losing any heat to the surroundings. That's why it's done in insulated containers. So that all of the heat exchange is happening between the water and the reaction or process that we're interested in. We also assume, and this is very important for setting up our equation, that all the heat lost by the reaction is gained by the water, if it's an exothermic reaction, or vice versa, all the heat that is gained by the reaction is lost by the water. In order to determine how much heat has moved, we use the specific heat equation, which gives us an idea of the heat absorbed or released. The heat absorbed or released by the water is equal in quantity but opposite in sign as the heat released or absorbed by the reaction, as I just mentioned in the previous slide, and it might become clearer as we do a calculation. Remember that when energy moves out, when it's an exothermic reaction and heat is released, we use a negative sign, and when it's an endothermic reaction, when heat is absorbed, it's a positive sign. So our specific heat equation, remember, is Q equals Cm delta T or Mc delta T, depending upon which way you want to write things in order. So let's do a calculation and hopefully it'll all become clear. This says a 100-gram sample of an unknown metal is heated to 95 degrees Celsius. This hot metal is then placed into a styrofoam cup calorimeter containing 50 grams of water at 20 degrees Celsius. The water and metal come to a final temperature of 31.67 degrees Celsius. So the water has changed temperature from 20 to 31, and the metal we're assuming was at 95 when it started, and it also went down to 31 degrees. So we can use all this information to calculate the specific heat of the metal. But we don't start by calculating anything with the metal. We start by the water because we have a mass and we have a temperature change and we know the specific heat of water. So if we use our formula that Q equals Cm delta T and think, okay, we're going to calculate the Q of the water. Well, it's going to equal the specific heat of water, which is 4.184 joules per gram degree Celsius, times the mass of the water, 50 grams of water, times the temperature change. What was our final temperature? 31.67. What was the initial temperature of the water? 20 degrees. So then if you go ahead and do the math on this, we know there's been a temperature change of 11.67 degrees. So if you go ahead and do all of the math and cancel out all of your units and round to 3 significant figures, you will find that there has been 2,440 joules of heat absorbed by the water. We're assuming that this is the same amount of heat that is released by the metal, except that it's in the opposite sign. So that we can say that the Q of the metal is going to equal a negative 2,440 joules. Now we have a Q for the metal, we have a mass for the metal, and we have a temperature change so we can figure out the specific heat. So let's start by rearranging our equation so that we can calculate specific heat. So we say the specific heat is going to equal our heat change divided by the mass times the temperature change. And then plug in our Q for our metal is a negative 2,440 joules. The mass of our metal is 100 grams. And then the temperature change of the metal will be different than the water. It ends up at 31.67 degrees, but it starts out at 95 degrees. So the temperature change for the metal would be a negative 63.33 degrees. And remember, this negative sign really is more a function in these equations as which direction the heat moved. But you'll see we have got two negatives. We're going to end up with a positive answer. Notice also that we have a very large temperature change in the metal as compared to the change in the water. And this just is reinforcing the fact that metals typically have a low specific heat and it doesn't take much heat moving in to cause a temperature change. And that water has a high specific heat, so it takes quite a bit of heat being absorbed in order to cause a temperature change. So even though our Q's for both are the same magnitude, just different in direction, the amount of temperature change that results from that amount of joules of energy is quite different. So if you go ahead and do the math, we'll find that for the C value for the metal is 0.385 joules per gram degree Celsius. And as expected, this is a small number, reflecting the fact that this is a metal and it has a low specific heat because we're having a very large temperature change for the amount of heat that was transferred. So hopefully this helps you see how we can use the specific heat equation in calorimetry equations to figure out any of these variables, but in this case to figure out the specific heat of an unknown metal. And this finishes up this fourth video for Module 2.